I told you that we find ourselves in a world where we really want to understand our environment. We want to understand our business environment, political environment, economic environment, medical environment, and so on like that. And if we want to understand our environment, then we need to collect data, right? When we collect data, we need to have an appropriate statistical methodology in place to fit our data. And that is what we call model. And that was why I told model is a mathematical simplification of reality. But there are different kinds of model. If you actually, the very first thing you need to do is, what is the form of model you want to adopt? The form of model, another way to put the form of a model is just like, what statistical methodology do you want to use on your data? And that's what I mean by choose a form of the model. The kind of model you're actually going to choose depend on the research question, depend on your objective. We have linear model, we have quadratic model, we have polynomial model, we have different kinds of model, logistic, and so on like that. And that is the reason why you need to choose the form of a model. Then number two, after choosing the form of a model, the next thing is to fit the model to the data. But let me tell you this. Before you can actually choose an appropriate model, before you can get the information you need from data, you actually need to choose a model that match the data. The state of the model and the state of the data have to be the same. Otherwise, it's actually going to be an exercise in futility. Okay? Now we need to fit data to the model to the data. And model and data, they have to agree. Okay? I'm going to say that again. Model and data, they actually have to agree. So you got to choose a model that will agree with your data. Or otherwise, you may not get information you need. Why do we fit model to data? I told you, we're looking for information. You know what? Information are not readily available in data. They are hidden. The kind of method you're actually going to use will depend on the amount of information you're actually going to extract from data. So when you use an appropriate model, then it means you have the chance of having the largest information. Okay? Now, step three. What we do in step three is to test the validity of our model. How do we know our model has really done the job? That is what we call model validity. Part of what we're going to be doing in this course. Whatever statistical model you adopt for your data, you need to be able to do what I call model validation. That is, how well does the model describe my data? I think the issue why we have problem at times in the world is not as if our models are failing us. Our models are not failing us, but we're not doing the right thing. Some of us, we don't even investigate whether the model that we have chosen will do the job. So we have a way in statistic analysis, in data analysis, we have a way to test for the validity of the model we are adopting. You know what? Every statistical model has assumptions. and assumption lead to limitation. And that is the reason why somebody said there's no perfect model anywhere, because every model has assumptions. And you know what? If you are assessing the validity of a model, all what you're going to do is to investigate whether assumptions underlying the models are violated or not. Sometimes we normally rush to take conclusion without revisiting whether assumptions underlying the particular models are met. I think that is part of what I'm actually going to walk you through in this course. Whatever model you choose, how do we investigate whether assumptions are violated or not? Take a look at this. I said a model is as good as assumption putting it to a model. If you want to know whether a model is fantastic, of course, you need to investigate whether assumption hold. Finally, if everything is good, if your model pass, okay, the next thing you're actually going to do is to use your model to address the question that motivated you collecting the data in the first place. There's a reason why you collect data in the first place. You actually want to answer a practical question. Okay? So you can only, base your of policy formulation on recommendation from your research if and only if your model has passed a validity test. I'm going to give you an example right now. Take a look at what happened. The Pfizer, the Moderna, the AstraZeneca, they've claimed to develop vaccine for COVID. But you know what? Some of you will be wondering, it took a long time before FDA could approve that. Let me tell you this. FDA has a reputation. They don't want to rush to conclusion. Even if the Pfizer claim they have the efficacy rate of 95%, the FDA will do their job by investigating, the impact of their vaccine. That is part of testing assumption violation. Because at the end of the day, imagine recommending something that could be harmful to people. That would be disastrous. It doesn't matter the number of time it takes to figure that out. It doesn't matter at all. Okay. The next thing I want to talk about, what makes a model good? We have different kind of models. Some models are bad, some models are good. Okay? And that is why I said there are generally two different things that we want from our statistical model. What do we want from our statistical model? Number one, we want our model to describe our data well. Okay? A model that can describe our data well, then it means that model need to be in the same state with the data. I'm going to say that again. The state of our model must be the same as the state of our data. Otherwise, that particular model cannot describe the data well. If you happen to be my friend and somebody walk up to me, oh, and somebody try to describe you, I will know that I will actually know you are the one the person is referring to. Because of what? Because I know you well. That is a relationship with model and data. Before a model can actually describe, where describe the data, that particular model must agree with data. They must be in the same state. Okay? And let me tell you this. If I know you, even if you happen to be my friend, I don't know everything about you, but I know a good, a reasonable number of things about you, which means there's room for error. Look at that. There's room for error. Okay? No matter how the model describe the data, there's always room for error. But you know what? We are actually looking for model that will lead to drastic reduction in error. We're fine. Okay? That is the kind of model we want. We know model cannot be perfect. But you know what? And that is why in statistical analysis, when we are validating a model, what we investigate the error. And let me tell you this, assumptions that I talked about the other time actually centered on error. I'm going to say that again. Assumptions of a statistical model revolve around error. Can you guys confirm if you guys are still hearing me clearly? Okay, good job. You know, I'm calling this a party. This is a statistical party. If you don't understand my party, if you are not happy in my party, please let me know. What I'm dishing out right now, I'm dishing out statistical cookies, candies. If you don't have your candies, let me know. You know, you don't have your candies, mean you don't get what I'm explaining. Do not hide your feelings. Good job. The second thing we want from our model, we want you to generalize well to new data sets. Okay. I think a chat came in. Let me take a look at that. Somebody said, assumption of a statistical model. Somebody said, miss the last part. I don't get that. Can the person yeah, okay,
A statistical model, something about error.
exactly. You know, statistical model, assumptions of statistical model revolve around error time. Does that make sense?
Yes, it does. Thank you.
Okay, good job. Thank you so much too. Okay, so the second thing is that we want a situation whereby our model can generalize, okay, well to a new data set. What do I mean? We want its error to be as low as possible when we apply it to a new data set. If I know what happened yesterday, you know, maybe I'm into sales, okay, and then I actually want to make a prediction about what the sales is going to be in the future, okay. If I introduce, oh, that is not going to be, don't let me use that. That's not a good example. Let me take you to um medical diagnosis where I have a model, and that very model I've applied it on data, and that very model is a very good model for diagnosis. Now, that particular model can be used to diagnose a new data, a new person. It's, you know, if I use a new person, if I want to know whether the person have a disease or not, that model, even though when I was building the model, that particular person was not part of the data I use. But you know what? If our model is good, it should not be only good to the data that we use in formulating the model. It should also be good to outside data. I'm going to call it outside data, to a new data. Because what we want to do is statistics, we want to generalize. But you know what? Sometimes it could turn out that these two features can often be in conflict. Okay, they could be in conflict. But we just wanted to know what makes a model to be good, and that's part of what you're going to learn in this course. Okay, um, I want to take you into an application right now where we want to talk about financial incentives. Financial incentive can improve initial weight loss. Okay, we examine whether financial incentive can improve weight loss maintenance. You know, the obesity rate in the United States increased drastically between 1930 and 2004 because of the increase in the obesity rate in the United States and Canada, not only United States and Canada. And that is the reason why um, they actually they want people to have a weight loss, but it is not everyone that are interested. And therefore, They want to use something to, what we call financial incentives. If we give you money, I ask you to lose your weight. Are you ready to do that? That is what this application is talking about. So we want to see whether financial incentive can improve initial weight loss. So which means we examine whether financial incentive can improve weight loss maintenance. Now take a look at what I have here. Okay. Wait, this data set here is after 4 months. Some people were given financial incentive. Okay, look at that. Some were not. Look at that. Okay. Now financial incentive in pounds and control means no financial incentives. Okay. Now what I recorded right here is just the difference between the initial weight and the weight after 4 months. I'm going to say that again. The difference between initial weight, okay, and the weight after 4 months. That's what we're talking about. After 4 months, the difference between the weight and the initial weight, we put into consideration your initial weight when we started, and after 4 months, we record the weight again, then we subtract. Of course, we have two groups right now: those who receive financial incentives and those who do not. The essence of this research is actually to investigate whether financial incentives could lead to weight loss. Now, I provided an arrow code right here in this course. You're going to be making use of the arrow software. Look at the way this is how to input data manually into R. For incentives, I put the weight loss right here. For the control, I put the weight loss right here. Of course, I got two population. When you have two population and you are looking at the difference between two groups, what are you going to do? Of course, you're going to do a t-test. Okay, you're going to do a t-test. You've done this before this, probably you the prerequisite, what qualify you to take the course right now. We got the knowledge that you have taken the t-test before. Okay, so now it's actually going to be t-test control incentive. Take a look at that. And I'm going to show you the result right now. If I were you, you can just copy this into R. When you copy this into R, you're actually going to see the result. Now take a look at the result. This is the result right now. And what I want to do now, I want to interpret this result. And I want you guys to pay attention. Okay, if you want to interpret, we're going to look at the p-value. Let me tell you this. Before you can interpret this result, you need to be able to know what is your non-hypothesis, what is your alternative. Okay, the non-hypothesis is just that there's no difference in the weight loss. Okay, when you put into consideration control and financial incentives. Okay, there is no difference. There is no difference in weight loss. There's no difference in weight loss. Okay, for the two groups. That is the non-hypothesis. Alternative means there is a difference. Okay, there is. I think I'm not going to say there is no difference. I think I'm going to say there is no significant difference, because let me tell you this: whether you are talking about non-hypothesis or we are talking about alternative hypothesis, different exists. But in the non-hypothesis, we're going to say there is no significant difference. Okay, in the alternative, there is a significant difference. Okay, now after stating this, then you're going to go to the p-value here. Of course, when the p-value is less than alpha, what do we mean by alpha? Alpha is a level of significance. And when I say level of significance, I mean the maximum probability of committing type 1 error. Okay, the level of significance can be given to be 5%, it can be 1%. Okay, generally speaking, we normally use 5%, 0.05. Okay, and you know what? The p-value here is 0.000005889, and that is less than 0.05. Okay, level of significance. Then because of that, we're actually going to reject the null hypothesis. Rejecting the null hypothesis in this situation means there's a significant difference between the two groups, with regard to weight loss. Okay? That is where if you want to use a p-value. But if you don't want to use a p-value, I want you to pay attention to this right now. What can you see here? Confidence interval. What does that mean? The confidence interval actually put into consideration margin of error. Okay, the confidence interval puts into consideration margin of error, and you know what? If the interval includes zero, if confidence interval includes zero, that means not significant. But if interval does not include zero, that means significant. So what can you talk about here? This from negative to negative. From negative to negative, that does not include zero. What can include zero is when you have from negative to positive. But right here, take a look at what I cycle right now. You get a minus 18, 0.05026 to minus 5.46058. This does not include zero. And if a confidence interval does not include zero, then you're going to reject the null hypothesis. So what I just showed you right now, there are two ways to take decision. It's either you use a p-value to take a decision, or you use a confidence interval to take a decision. The two agree. Okay? When the p-value is less than alpha, that is less than the 0.05 level of significance, you're actually going to reject the null hypothesis. When the confidence interval does not include zero, then you're also going to reject the null hypothesis. Does that make sense to everyone? Is there anyone who needs clarification on this? Is there anyone?
I have a question about the initial setup. Do
Okay.
we have to like say to R if it's equal or unequal variance for the t-test?
Oh, that's a very look at me. Look at me. Good job. Good job. We also have assumption for this test as well. We have assumptions of equal variance, that the variances, the population variances of the two groups have to be the same. That's an assumption. The moment that is violated, okay, so then your result will be misleading. So what I will advise that you do is you can run that for equal variance and see what is going to happen. Okay, so you have that's a very good observation. Okay, but the reason why I did not talk more about that because of the fact that the essence of this course is basically looking at the effect of one variable on the other one. And that's why I don't want to go more into that. But what you just said right now is absolutely correct. Okay. Now, that is the end of this material. Like I said, this is just outstanding from what we did on Monday. Is there anyone that have question before I go into today's material? Is there anyone that have another question? Okay. In the absence of that, I'm actually going to share my material with you guys right now.